And then we ended, I don't think we talked about neutralization. We ended with defining some terms, acidic and basic, based on this kind of unusual reaction where two water molecules react with each other, making hydroxide and hydronium. So the water molecules ionize to form hydroxide and hydronium. And then we said that you can actually measure how much of each of these there are, and you get these really small numbers of each of them. And since that's how it exists in pure water with exactly the same amount of hydroxide and hydronium, we can define something as acidic or basic simply by looking at the balance of those two molecules. So an acidic solution has more hydronium than just water and less hydroxide. And a basic solution has less hydronium and more hydroxide. Okay, so here's where this idea of pH comes in. Those numbers are a little bit unfriendly to work with, let's say. They're really, really small numbers. They're always in this scientific notation because they're so small. So it would be a lot easier if we could simply compare them as normal integers or other types of numbers, smaller, different numbers, instead of these scientific notation things. So this is where pH comes in and why we use pH. The pH is a calculation. It is the negative log of the hydronium ion concentration. So who remembers logs? Everybody's looking at me like, come on, that was a really long time ago. No log fans here? Does anybody know what a log does? Did our excellent education system instill in you lifelong knowledge of log functions? Not so much. Do you know how to do a log calculation? Push the button on the calculator. Yeah, that's how you do a log calculation. And that's not like that's how you do it. There's no like longhand way to do it. There used to be, even in the old days before calculators, there were log tables, and you had to look up the number basically, because you can't. There's no easy way to do that calculation. But with simple numbers, we can do it, because what a log really is it's returning an exponent. So it's saying, take this number that is 10 to some exponent and give me just the exponent. That's what a log does. It's like the inverse of raising something to a power. So to show you what that looks like, if we take the log of 10 to the minus 7, we get minus 7. If we take the log of 10 to the 7, we get 7. And that's the same with those whole numbers also, or the numbers as we wrote it up there as well. So log of 1 times 10 to the minus 7, 1 times anything is just itself, right? So that is also just negative 7. So you're getting the exponent back. Now that's super easy as long as the number is just 10 to the something. When there's other stuff in front, like if instead of 1 times 10 to the minus 7, it's 3.4 times 10 to the minus 7, well, now we have to use our calculators, because now we're not going to get that to work anymore. So, yeah. Acids and bases, yeah.
So we weren't supposed to learn that yet?
Well, we haven't yet. Why did you? Okay, well, good. You're ahead.
This quiz was going to be about.
No, same. So, okay, so can I skip all this then, or you got it?
No, we read that. Like the part was supposed to. I read the part that was.
That's what I thought this quiz was going to be about. Okay.
Okay, well, good. You got extra preparation for the exam next week.
It's for the Wednesday exam. There.
A week from Wednesday.
Oh, okay. Oh, next week, not this.
Right. Right? I think that's right. Now you're figuring me out. The 24th, right? Is the exam? Yeah. Not the 17th. Right. Yeah. All right, so back to logs. So that's how you do it. In this class, we'll mostly be doing our logs that way because not everybody has a scientific calculator, and the calculators we have for the class are not scientific calculators. So we won't have to do any special log calculations on exams. But just in case you need to do it, let me show you the best way to do that. Does anybody have a writer calculator?
Yeah.
I'll show you how a couple different calculators do these things so that when you run into these in the homework or whenever, you can do it. See if we'll get started up here. Okay. So if you have this sort of a calculator, scientific notation is kind of nice. So if we want to type in 1 times 10 to the minus 7, on this kind of calculator, you don't want to type in 1 times 10 to the minus 7 because it'll probably get messed up in the order of operations. The easier way to do it is there's this little function that is EE, and that's what that means. So you can go, both those things. Okay, so I would go 1 EE negative 7, and that means 10 to the negative 7. So a lot of calculators have this notation, not just the graphing ones, but the regular scientific ones too. That's one way to do it. So if you want to take a log of that, you go log, and then 1 EE negative 7. And you get negative 7, just like what we typed out. All right, see how that works? So if you want to do a pH calculation, the pH is the negative log of the hydrogen ion concentration. So it's negative log 7 and 7. So you just flip the sign because the negative of a negative is a positive. So for any of these even numbers, we should not need a calculator to do this. But if you had something like, if your hydrogen ion concentration was something like one of these that they given the examples in the book, 6.5 times 10 to the minus 5. Let's say you want to know the pH of that, so you go negative log of 6.5 times 10 to the minus 5, and your pH is 4.187. So that works. All right. Other scientific calculators, like I think the one on the computer here, it's a little bit different because if you try to click log, it says invalid input. And these types of calculators, and you may have one also, you put in the number first, and then you push what you want to do the operation on. So in this one, we would go 1 times 10 to the, nope, not that, because it's still backwards. Sorry. So we put in the exponent first. So we'd say negative 7. Nope, 7 negative. Take that to the 10, and then multiply it by whatever we need to multiply it by. So let's just say 1. And then we take the log to get our negative 7. So it's backwards. You put the number first, and then you negative it, and then you 10 to the it, and then you log it. So if we did that for that same one, 6.5 times 10 to the minus 5, if we want to know the pH, we'd go, we'd start with that negative 5. So that's our exponent, 10 to the minus 5. we go 10 to it, then we multiply by 6.5, then we take the log, and then flip the sign of that log. So it would be 4.187 backwards. And if you have questions about your individual calculator and how to do that, I can try to show you if I can figure it out. All right, so that's where pH comes from, the negative log of the hydrogen ion concentration. But you'll notice up here that when we do this, when we talk about water, we also have this hydroxide ion hanging around. And as it turns out, because of the reference of pure water, the product of the hydronium and hydroxide concentrations is always the same number. So if we multiply the hydronium concentration of any solution by the hydroxide concentration, we get the water dissociation constant, which is 10 to the minus 14. So that means we can also calculate a POH, which has the same calculation, but just with a different number with the hydroxide concentration. And so another way that we can state that equation that we just wrote is that the pH plus the POH equals 14. So the pH and the POH will always add up to 14, which means if you know either the hydroxide concentration or the hydronium concentration or the pH or the POH, you can always calculate all the other ones. So let's practice that. All right, so here's an example. We have a solution that has a pH of 3.5. Calculate the POH, the hydrogen ion concentration, and the hydroxide concentration. So we can do all of that just from knowing the pH of 3.5. Okay, let's see how we do this. So for me, I think the easiest one, the one that I always remember, is just that one that the pH and the POH is 14. So rather than mess with multiplying these tiny scientific notation numbers, let's just add and subtract because that's easy. So if the pH is 3.5, what does the POH have to be? 10.5, right. So the POH is 14 minus the pH, which is 14 minus 3.5, is 10.5. Okay. So POH and pH added together equal 14. So what plus 3.5 is 14? Well, 10.5. All right, so now we've got the pH and the POH. We need to get the hydrogen ion concentration. So if we want to do the opposite of the log, what's the opposite of a log? Opposite of a log is raising something to a power of 10. If the log gives you the thing that was up in the power, up in the exponent, then the opposite is to raise it to the power of 10. So to get the hydrogen ion or hydronium ion concentration, we're going to take that 3.5 and raise it to the power of 10 and put a negative on there. Hopefully this doesn't get too messy, but I just want to show you this number comes from there. The pH comes from the hydronium ion concentration, so we can get the hydronium concentration from the pH. Now, if you don't have a calculator, like on the exam or something, and I ask something like this, it's fine to just leave it like that. Usually we don't leave exponents with decimal places, but if you don't have a calculator that can deal with that, you can leave it like that. It's no problem. Otherwise, you could calculate it. So we would go negative 3.5, whoops. Negative 3.5 raised to the power of 10 is 3.16 times 10 to the minus 4. And remember that that's a concentration. So that's in molar. That's a molarity of the hydrogen ion concentration, or the hydronium ion concentration. All right. So we can get the hydroxide concentration in the same way using the POH. The hydroxide concentration we grab the POH. And then do that calculation. And just looking at this before we finish, would we expect this number to be bigger or smaller than the hydronium concentration? Got it? It's tricky because there's like negatives in the exponents, and it's going to be smaller. Yeah, it's going to be several orders of magnitude smaller. So let's do that. 10.5 negative, and then raise to the power of 10. 3.16 times 10 to the minus 11 molar. That's how you can calculate all those different things given one of them. Okay, let's try another one. You try one this time. I'll just leave that stuff up here. We'll do another one over here. If your hydronium ion concentration is 1 times 10 to the minus 9 molar, calculate the pH, the POH, and the hydroxide ion concentration. So the other three. Use the reference in what we just did and give it a try. Work together if you want for this one. Let me know if you So do you need a calculator for this one? I mean, you can use it, it's fine, but you probably don't need it because it's a nice even number. If it weren't a nice even number, then we'd want to use the calculator. All right, so what is the pH? If the hydronium ion is 1 times 10 to the minus 9, what does the pH have to be? Just 9, right? You take the exponent. As long as it's a nice even number, you can just take that exponent, and that's the pH. So the pH equals 9, which means what does the pOH have to be? 5? Anybody get anything else besides 5? Got 5? Right, because it's got to add up to 14. So 9 plus 5 is 14. So the pOH has to be 5. All right, and then the last thing to calculate is the hydroxide ion concentration. So we're just going to raise the pOH to the negative, to be a negative power of 10. Or sometimes the way it's written, it would be 1.0 times 10 to the minus 5 molar. Either way is fine. Again, taking the negative of the pOH, raising 10 to that power, gives us the hydroxide ion concentration. All right. So let's think about what these things mean. Well, first of all, how much different is a hydrogen ion concentration between two pH numbers? So if we had a pH of 3 versus a pH of 4, what factor difference is that in concentration? And so it would be 10 to the minus 3 versus 10 to the minus 4. So that's a factor of 10. So that tells us that every number on that pH scale is actually a 10-fold increase in hydronium ion concentration. So that's what we call sometimes a logarithmic scale. So let's look at that pH scale. And I'll copy this over from the book so we can, because it has some nice references also. If I can still get here, yep. All right, so here's our acid-base scale. Oh wait, the numbers aren't there. Hold on, we gotta get the numbers too. That's not even the right picture. Hold on. Does this not have it? Okay, there it is. Let me get rid of that one. This one instead. Here we go. That looks a little better. All right, we'll zoom in on this a little bit. We can see it. So here's our pH scale. On the left, you've got the scale itself, and it's graphing it's showing the hydroxide concentration, the hydrogen ion or hydronium concentration, and then what that corresponds to in pH, and what would be an example of that. So down at the bottom or at the top, whatever you want to call it, of the scale is the most acidic solution, which would be 1 molar hydrochloric acid. If it's 1 molar, that means it's, or no, I'm sorry, it would be less than 1 molar hydrochloric acid, because if it were 10 to the minus 1, that would be a pH of 1. So that you're just talking about strong hydrochloric acid. As we decrease the hydronium concentration, you can see the hydroxide concentration increases by factors of 10. And we have some examples of what that stuff is. So our stomach acid is way down here at a pH of 1. Then we've got like the most acidic things that are kind of almost hard to eat, things like lemon juice. And then around 3 and 4 are most of the foods that we like have a little bit of acidity in them, and it's usually right in that range. So when you're talking about sweetened drinks, candies, all that, juices, sodas, that's all right here. The problem with that is that the threshold for teeth decalcification is right around 4.5 here. So if teeth are kept in that environment, the enamel on the tops of your teeth can start to wear away, and that makes it possible for bacteria to get in there. And that's why dentists always say don't drink pop and that kind of stuff, or don't drink like coffee with milk or sugar, because what you're doing is keeping your mouth in the state of low pH. The teeth can decay, and then if you have sugar also, like in a sweetened drink, that gives the bacteria something to feed on in your mouth, and they can kind of get their way in your teeth and eat up all the stuff, which is not great for you. So that's right in this range on the pH scale. All right, stuff in your body is usually somewhere around here, depending on where in your body it is. Blood pH in particular is really important to keep very tightly controlled. So blood says 7.4. We said 7 was neutral, but if you get your blood pH at 7, you're actually kind of in trouble. Your blood needs to be kept at a very precise pH of really 7.35 to 7.45, using a buffer, which we'll talk about in a second. And then onto the basic side of the scale, you don't see a lot of food stuff. We talked a little bit about that, how basic flavored stuff doesn't really taste great usually. So seawater is a little bit basic, tap water is a little bit basic. And then as you get more and more basic, you get into other stuff that is just as corrosive as what we saw before. So stuff like ammonia cleaner, oven cleaner, sodium hydroxide, which is really, really caustic. I don't know if we've used concentrated sodium. I don't think we've used that much sodium hydroxide, but just as caustic as any kind of strong acid. You don't want to get it on your hand. And it's used for cleaning also. Not much here used in food, with some exceptions, like pretzels. The outsides of pretzels turn really dark brown because they're cooked very briefly in a basic environment. If you've ever made like a corn dough out of dried corn, it's called masa. You use actually something like soda ash, calcium hydroxide to treat. You soak these, soak the dried corn in a basic solution, and then when you grind it, it kind of releases a lot of, breaks down some of the proteins and molecules in there, and it allows you to break it down into that flour that makes delicious tortillas and tamales and all that stuff. But there's not a whole lot of examples of basic foods in cooking. All right. Yeah. Do people not?
Huh?
I thought that was just like is that not like a universal thing?
What?
Who doesn't like tamales?
I don't know.
Really? I don't know. I mean, right? I don't know. Yeah. Do you?
Yeah.
Yeah. Okay.
Oh yeah.
All right. So that's basically pH scale. Let's talk a little bit about blood and about this idea of buffering. We'll talk about this more when we get into the chapters on enzymes and proteins. Have you heard the term buffer, or have you ever used a solution of something like that said buffer solution or something like that in a health context? A buffer is any solution that can maintain specific pH. So one misconception with buffers is that they're always neutral, and that's not true. You can make a buffer at any pH you want, But the point of a buffer is when you add more acid or base to it, it keeps its pH. It stays at that specific pH. So let's see if they have the example in here. No, I can't find it in here. So if you took pure, oh, maybe it's here. No, I thought I saw it, but never. If you took pure water at a pH of 7, and you had like 2 drops of hydrochloric acid, concentrated hydrochloric acid, it's going to immediately become very acidic because you've added that hydronium, and really nothing else happens except the hydronium goes in, and that would drop the pH all the way to pretty much 1, with just a couple drops of really concentrated HCl. If you add HCl to a buffer solution that's buffered at 7, it will stay at 7. It will drop just almost like imperceptibly below 7, but it'll basically stay at 7. So a buffer is a solution that allows that can maintain the pH. And the reason that it works that way is really interesting, but I don't think we need to get into it here, and we're kind of getting low on time. So with other stuff that we need to talk about tonight. So it's not in the objectives. You don't need to know the specifics of how buffers work. If you're curious about it, they talk about it in the book, or I can explain it to you sometime. It's pretty interesting, but it's just any solution that can maintain a pH. And that's really important in biological scenarios because changing drastically the pH in your body and various parts of your body, like your blood, really messes with all the stuff that needs to happen. Most of the reactions are meant to be done at a particular pH in your body. Most of the proteins exist, the amino acids exist in their structures at a particular pH, and if you change that, it's actually going to change the structure completely. So you have to keep this really careful pH control. Does anybody know what keeps the pH control in your blood? What molecule is mostly responsible for it? Guesses? What is it? Oxygen's a good guess. No, try another one. Carbon dioxide, yeah, that's the one. So when carbon dioxide reacts with water, it makes, carbonic acid, which is H2CO3. And then carbonic acid can be deprotonated by more water. So wait, this is going to look weird if I do it this way. So that carbonic acid, by the way, this goes both ways. Can react with more water to make its conjugate base, which is bicarbonate, and hydronium. So the more carbon dioxide that's in your blood, the more hydronium that gets produced. And as carbon dioxide comes out of your blood, then it goes the other way, and you're actually consuming hydronium. So that's one way that the body can maintain its pH is by making sure that the appropriate amount of carbon dioxide is being dissolved in your blood. What's one situation when you don't have enough carbon dioxide in your blood? Why do you not have enough carbon dioxide in your blood? If you're having respiratory issues, yes. What kind of issues? Think of one? Oh, sure, like, yeah, specifics. I was thinking more like in general, but yeah. Well, things like that have, the bigger problem is getting oxygen in, but there's also a problem if you are having trouble getting the carbon dioxide out, specifically getting too much of it out. And one common condition of that is hyperventilation. If you're breathing too hard, you're exhaling too much carbon dioxide, and that's causing your blood pH to get messed with. It's a situation called alkalosis. You can also have acidosis if there's too much acid. So that pH gets out of that 7.35 to 7.45 range, and suddenly, you're feeling weird and having some problems. And so you need to just relax, start breathing more steadily, and get more carbon dioxide dissolved into your blood so you can get back in the right pH. So that's how buffers work. I think that's probably a good place to stop and check the objectives, make sure we got what we needed to. Yeah, I think that's good. So let's take a break there, and we'll come back and talk about organic chemistry. And we're done with the math, so we're not going to do any more calculations. Congratulations. All right, so we're going to change gears completely here. Start talking about organic chemistry, which seems very different from the stuff we've been doing. Hopefully different in a good way. We'll see. The book doesn't quite organize their organic chemistry part the way we're going to do it. They have it kind of set up. I don't know if you ever noticed this, but it's by color. If you ever saw a hard copy of the book, there's like purple for the stuff we've been doing, the basics, and then there's blue for organic, and then different blue. That's not blue. That's green, aqua, something. I don't know. And then a different color for the biochemistry. We're not going to really get in depth with all of this stuff. We're going to talk, spend a little bit of time on chapter 10 talking about the basics and like the kind of stuff that you should know. And then we're going to sort of zoom right through all the rest of those next 5 chapters, really not doing much of it at all, and then getting into the biochemistry stuff in a couple weeks. So let's look at this. So does anybody know why it's called organic chemistry? This is what? Yeah, but what does that mean? It's the original?
Yeah.
No chemicals? Then why would it be organic chemistry? It's a good idea, though. Sort of. Yeah. Yeah. Well, so it's kind of a silly distinction. It comes from, like, the word organic means having to do with life. So it has something to do with coming from living things or studying or being about living things. And it comes from back in the old days, it was thought that there was a clear line between living things and non-living things. Like the materials and the chemicals that were in living things could never be in non-living things and vice versa. So only living things with life, or whatever you want to call it, could produce these types of chemicals, and minerals and other sorts of things like that could never produce those same chemicals. And now we know that's not really true. Living things get their material mostly from carbon dioxide and air and water, and we can cross all that stuff. But this name organic chemistry stuck as mostly pertaining to molecules and compounds that somehow interact with life. So they either are things that are going to go in your body, or they're something that is interacting like with some other living system. That's not totally true. Fuels are all organic. We don't drink a lot of gasoline, but that's basically the idea. So now we define organic chemistry a little bit differently as molecules based primarily on carbon. So we're talking about the chemistry of mostly carbon-containing molecules. And we're going to look, I mean, they have lots of other stuff in them too, but the basic structure of the molecule is based around carbon. All right, so let's look at carbon. Let's remind ourselves a little bit about how carbon behaves. Of course, its symbol is C. How many valence electrons does carbon have? Yeah, 4 valence electrons. So that means how many valence electrons does carbon need to have a full shell? Yeah, it needs either lose 4 or gain 4 to form an ion. It doesn't really form ions, which we've talked about before, but it does like to make connections with other stuff to get those four things. So we could take a carbon atom, and it could bind with some hydrogen atoms, which each have 1 electron. We could make some covalent bonds sharing those electrons. So carbon has its 8 and hydrogen has its 4. Or I'm sorry, carbon has its 8, hydrogen has its 2. Each hydrogen has its 2. So from this, we can say that carbon generally makes 4 bonds. And one of the nice things about organic chemistry, the chemistry of carbon, is that it's pretty predictable. And one of the things we can predict about it is that carbon's going to have 4 bonds. So when we're trying to figure out what is this new structure, what does this molecule look like, we can make the assumption that carbon's going to have 4 bonds. It's not true in every case, but for the ones we're going to see, it is true. So let's think about what that's actually going to look like. One way we would draw that maybe in a couple chapters ago is something like this. That's not really quite what it should look like. So grab your model kit and get one of the little black pieces. These represent carbon atoms. And you'll notice it has 4 holes in it for the 4 connection points. So take one of those and put one of these sticks, which are the bonds, in each spot. And some kits have been kind of mixed and matched, so that you can find 4 sticks that are about the same size. That makes it work a little bit better. If you don't have that, don't worry about it. And then we're going to use the little round spheres, the little blue ones here, to represent hydrogen atoms. So put one of those on each end. You should have to go like this. All right, so you got this. If you were to draw this, would you draw it the way I drew it there? If somebody gave you this and said, hey, that's C, that's H, draw it. Is that how you would draw it, you think? Probably not, because it's not really reflective of the shape, right? It's kind of has a neat shape to it, and that doesn't really show that. So we're going to draw this in a way that does reflect its actual shape. By the way, this molecule is called methane. And we will use this notation. There's nothing wrong with drawing it this way. But we have to just understand that it doesn't reflect the actual structure of, or the shape of what this thing would be. So if we want to draw it more like what it would look like, we either have to have pretty good 3-dimensional drawing skills, which maybe you do, or we have to have some sort of convention that shows us or tells us what that 3-dimensional shape looks like. So I'm going to pull this up on a program here so I can put it in the notes. It's called M3D. Oops. So I can do this on the screen like this. So that's that same kind of molecule that we all just built, right? And the way that we draw this on paper is we imagine kind of looking at it sideways like that. And if you're looking at it sideways like this, and you can straighten that up there. You can do this with your model too. So you've got the top one and the one going off to the left, or the right, sorry, in the same plane. And then the other two are kind of like one's coming out at you and one's going back. See that view? All right, set that down. Think about that view, and then we're going to draw it. So I'm going to offset this one a little bit so we can see all the pieces. Copy it into the notes. And the way we're going to draw it is we'll put the C here. just like we did before. And we'll draw one hydrogen going up and one going out like that. And then for the other two, we'll use some notation to show that one of those is actually meant to be coming out of the paper and the other one is meant to be going back behind. And the notation we use is we use a wedge-shaped bond like this that's colored in to indicate the one that's coming out. And then we use a dash line like that to indicate the one that's going back. And it doesn't matter which ones you draw to the right, which ones you draw to the left. But if you rotate this, you'll see that the wedge and the dash are always on the same side of the molecule. And the straight line is always on the other side. So you can do it this way, like that, or you can kind of rotate it around, do it the other way, but you still have the wedge and the dash on the same side. And as we'll see in some larger molecules later, this actually matters because when molecules become less symmetric, there can actually be a difference between what's on the wedge and what's on the dash. That can actually make a different compound. So we have to be a little bit careful of that. But the key takeaway here is that carbon is in this particular shape, which is called a tetrahedral shape. Each of those hydrogens is at the corners of a solid called a tetrahedron, kind of like a pyramid with a triangular bottom, where they're all equivalent. And that angle between bonds here is right around 110 degrees. All right, so that's the basic structure of carbon itself. And when we see all these molecules with carbon atoms in them, as long as they have 4 bonds, 4 different things, 4 atoms connected to them, they're going to have this type of geometry, and that's going to influence how we draw them a little bit. So let's look at some larger molecules now. We're going to separate the molecules we look at into different classes based on the types of molecules that are connected. And the first class we're going to look at is called alkanes. Alkanes are molecules that are only carbon and hydrogen with no multiple bonds. They're only made of carbon and hydrogen with no multiple bonds. And that means that we can start building them up. We're going to make a table to do this. So we'll have their name. Molecular formula. And then we're going to look at drawing their structures in 3 different ways. The first way we call the Lewis structure, which is the way that we've been drawing all this stuff. Then we're also going to look at something called a condensed structure. And then we're finally going to look at the line structure. And this may not all fit when we get into some bigger ones, but we'll figure that out when we get there. Okay, so let's put in the one that we know so far. Methane. Methane is CH4. And we can draw its Lewis structure just to not confuse everybody here. Let's just draw it in its flat form. We'll get back to that dash and wedge notation later. Let's just look at its flat form here. For methane, the condensed structure is actually the same, and there is no line structure. So none of that really makes sense until we get into some bigger ones. The next one in the group is called ethane. This one's going to have 2 carbons and 8 hydrogens. And remember that carbon can only have 4 bonds and hydrogen can only have 1 bond. So there's only one way to draw this structure, and that's this. All right, so now let's talk about what this condensed structure is. As you'll see in a little bit, as these molecules get bigger, it becomes really tedious and annoying to draw every atom and every bond coming off of everything. So there are ways that we shorten that up, we abbreviate it to make it easier to draw. And the first way is the condensed structure, where the hydrogens get condensed onto the atom they're connected to. So instead of drawing a line with every hydrogen coming off of it, we just say, here's how many hydrogens are on this atom, here's how many hydrogens are on this atom. So it looks like this. It's kind of like a formula, kind of like a molecular formula, but it gives us more information because it actually shows us how they're connected. And it says that these 3 hydrogens are connected to this carbon, and these 3 are connected to this carbon. And actually, this is going to get confusing, so I'm going to delete that one up here. All right, and then the line structure looks like this, and I'm not going to explain it yet. Let's get a few more lines, and then we'll go back to talking about the line structure, because that might take a little work. Okay, next one on the list is the third one. Propane, which is C3, not H10, sorry. Hold on, this is not H8 either, sorry. So correct the one above, that should be H6. And propane is C3H8. 3 carbons. Again, there's really only one way to draw this if we want that many atoms. So for the condensed structure, we are going to, again, condense the hydrogens onto their carbons. And that looks like this, CH3, CH2, CH3. Because this carbon has 3 hydrogens attached to it. This carbon has 2, and this carbon has 3. So 3, 2, 3. The line structure for propane looks like this. Supposed to be a straight line, that's why I keep deleting it there, okay. All right. So the next 2 on the list are called butane, and pentane. And I want you to try to fill in this rest of this table without getting any more information. Try not to look anything up. I will give you a hint. Start with the Lewis structure. Follow the pattern of what we've been doing. And then see if you can find the molecular formula and the condensed and line structures too. If you can't, that's okay, but give it a try. Try to get as much filled in as you can. You can work together or ask questions on this. Look back at the ones we've already done. Try to follow the pattern. All right, so it looks like most of you got this. I will fill in mine as well, and then you can check if you got any inconsistencies, but the ones I saw look pretty good. And so you can probably also see how it starts to get tedious to draw those structures out in the Lewis structure form once you get more and more carbons. Again, don't worry about the Lewis structure or the line structure thing. We'll get to that in a minute. But even the condensed structure is a lot easier than drawing everything out like that. All right, so let's look at these structures in a little bit more detail. So these line structures, we're going to spend a little bit of time on because they're by far the easiest and most convenient way to express organic structures, how molecules are connected in carbon-based molecules. It's how it's used almost exclusively in this type of chemistry. If you look up structures of drugs, or you like open little drug fact pamphlets from your medication, these are the types of structures that you'll see. It's way easier once you know how to do it than dealing with those other types. So we're going to use it quite a bit. In line structures, let's just take that last one to show what we mean here. I'll just copy this over. Again. All right, so we've got our Lewis structure, condensed, and line. So where do you think the carbons go in the line structure? Carrying those three. Where are the carbons? I mean, they're not, the C's aren't shown obviously, but can you tell where they are? Yeah, they're at the ends and the points of the line. So if we number these out, 1, 2, 3, 4, 5 for the 5 carbons in pentane. In our condensed structure, we've got this. And then our line structure, we've got this. 1, 2, 3, 4, 5. So in line structures, carbons are at the ends and the intersections of lines. And there's a couple of reasons for the zigzagging then. One is just because otherwise we wouldn't be able to tell where the carbons were. So you need that inflection point to say, okay, there's one here and there's one here. If it were just straight, there'd be no way of knowing. But if we go back to our models, that also actually reflects the real geometry of these structures. If you connect a couple carbons together, I'm going to take the hydrogens off right now so we can see it better. So if I connect 4 carbons in a row, you can see that that is actually the shape that it would make. I'm not showing the hydrogens. It's not a straight line. It's a zigzag because of the bond angles of that tetrahedral structure. So with line structures, not only do we get a more convenient way of drawing, but we also have a better reflection of what the real shape of that molecule would be. The second thing about line structures are the hydrogens attached to carbons are left off or omitted. And why is that? So why don't we lose information by leaving the hydrogens off? How could we tell if we had a line structure? How could we go back and tell how many hydrogens were there? Right. Right, because we know that carbon always has to have 4 bonds. So if all the other bonds are shown, we can just assume that there's enough hydrogens to fill in the blanks. There would be 4 bonds. So let's try that. I'm going to give you a more complex line structure, but we're going to try to figure out what the molecular formula is. So there's a line structure. Let's figure out the molecular formula, that is how many carbons and hydrogens it has, by counting them out. So the carbon part is, well here, why don't you try it first? Take that structure and see if you can write down how many carbons and how many hydrogens. Then we'll do it together and see if you're right. So how many carbons did you get? How many hydrogens? Did you get? Plus. Oh, sorry. Okay, where's that?
I said 28.
No, that's way out. Somewhere in the middle there. Let's count them out. I think that's right. So let's see. We got our 8 carbons. That would be here. I'll cut them off here. 1, 2, 3, 4, 5, 6, 7, 8. Yep, 8 carbons. All right, so now for the hydrogens, remember each position needs to have 4 bonds total. So we take however many bonds are shown to the other carbons, And then we add hydrogens in until we get to 4 each position. So if we look first over here, this carbon has 1 bond shown, which means it needs how many more? 3, right? So we can draw those in 1, 2, 3. And then that's going to be the same for every end of a line. Okay, we can do this one too. And this one. All those ends are going to have 3 hydrogens. All right, so let's look at some of the other ones. What about this carbon right here? How many hydrogens there? Well, how many hydrogens just at that position? We got some different numbers here. Well, let's see. How many bonds is this carbon already connected to? 1, 2, 3, 4, right? So does it need any hydrogens? It doesn't. It's full. It's good. So there are no hydrogens at that carbon. So we move on to this one. How many hydrogens here? Should be 2 more, right? Because we got to get to 4 total. And that leaves 1 more spot. Right here, how many hydrogens there? Yeah, just 1. Okay, so we count all those out. And I believe you get 18. So the formula is C8H18. All right. The last rule, which we haven't really talked about because we haven't seen any other types of structures, but we'll get into it later. Other elements like O or N or whatever, things that aren't carbon, are not abbreviated. We need to remember to keep their hydrogens showing. So we don't take off the hydrogens on other types of atoms. The reason for that is that none of the other atoms are quite as predictable as carbon. So if you leave a hydrogen off of an oxygen or a nitrogen or something, you actually do have a different structure, or you could have a different structure. So we have to make sure to actually specifically show each of those. So let's try another one. I'm going to draw another big molecule, and I want you to try to find the formula. What? All right, a couple of things going on in this one. So we've got some different atoms that are not carbon. And we've got some double bonds. Just like in the smaller structures that we looked at a few chapters ago, double bonds count as 2 bonds. So when you're looking at those carbons, those double bonds coming off of the carbons count as 2 bonds. So what? Okay. So same question, try to find the molecular formula for this molecule. Count up the different atoms and figure out how many of each there are. Once you think you've got a number, ask the people around you, see if you came up with the same numbers. If not, try to figure out why. Well, so you've got a carbon on the bottom of that, right? And there's another carbon coming off that. And then it's double bonded over to the other one. And then bonded down to the nitrogen. So there isn't a carbon in the very end. All right, so because of time, I want to go on. But with this one, a couple things to take note of. We're going to go through it. But one thing that sometimes confuses people is when you have other things connected, like the nitrogen or the oxygens, you don't also have a carbon at the end of that line. So the carbons are only the ends of the lines where there's nothing else. If there's another atom there, that's what is there. There's not a carbon there. So our carbons here, I'm going to number them so we can see them all. Our carbons here are going to be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Eleven carbons in this molecule. Is that somewhere close to what you got? Well, the ends of the double bond are carbons, but the bond itself is just the shared electrons between the two carbons, just like from before. So it's like C sharing two pairs of electrons with another C. All right, so then let's count up our hydrogens. I'm going to make little dots for the hydrogens. So we've got, don't forget the ones that are listed, that are shown. So we've got 1, 2, 3. And then, what? And then we've got the other ones connected as they're connected. So we have to go to each one. So carbon 1 has 3 bonds showing. So that means there's going to be 1 hydrogen there. Carbon 2 has 3 showing, 1 hydrogen. Carbon 3 has 3 showing, 1 hydrogen. Carbon 4 has 2 bonds, so that needs 2 hydrogens. 2 here, 2 here, 1, 1, 2, and 1. I think that covers all of them. So let's count it out. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17. All right? Anybody find more or less? I think that's right. What? Let me count up again. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17. And then we have a molecular formula, so we need to include all the atoms. So let's put the N and the O's in there too. Show there's 1 nitrogen and 2 oxygens. So that would be the full molecular formula that we found from the line structure. All right. So this takes a little bit of practice. The book goes through it and has some practice problems, but not a lot. So I'm going to put another section from a different book up on Blackboard for reference for doing this kind of stuff. And we're going to practice a little bit more now. Let's look at one more topic related to this, and then we're going to build some more models. Isomers. This term isomers. Isomers are molecules that have the same formula, but different connectivity, so connected in different ways. So they have the same molecular formula, but they are connected in different ways. So let me show you what that looks like with the models. The simplest molecule that has isomers of the alkanes is butane. So this is this 4-carbon molecule. I'm showing it without the hydrogens right now. So we all connected butane like this, 4 carbons in a line. And single bonds actually rotate. So this is the same molecule. Doesn't really matter how we put the thing. But there is another way to connect these and still have the same molecular formula. Do you know how you can do it? It's another way that you can connect these 4 atoms. It would actually make a different molecule. See it? So that's one idea, is to connect the ends together. But as we'll see, I guess probably not today, but another time, that actually is not an isomer because that makes a different molecule. Because by doing that, you take up some of the holes that used to have hydrogen in them. So that molecule would not have as much hydrogen. But there is another way to do it. You see? Yeah. Like this? Yeah. So that's the isomer. So this molecule still has 4 carbons. And if we counted it out, still has 10 hydrogens. But they're connected in a different way. They're fundamentally different. So let's draw those 2 molecules, those 2 isomers. And we'll draw them in Lewis structures and in line structures. All right, so there's our one, and let's draw all the hydrogens out too. All right, so there's one isomer. And the other one looks like this. Oops, I didn't leave enough room for hydrogens. They're both C4H10. So they both have the same molecular formula. Oh yeah, sorry. But they all but they have different connections. Thank you. If we were to draw those as line structures, the one on the left would be this, and the one on the right would be this. So those are the only possibilities for butane. Those are the two isomers of butane. So now your challenge is, the next few minutes, is try to find isomers of pentane. So if we add one more carbon on there, how many different isomers can we make? I believe there are 3 different ones for pentane. See if you can find all 3. You can try with models, so you can use, I would say do it without the hydrogens, just use the black balls and the bonds. And see if you can find all 3 isomers of pentane, of C5H12. Yep. Few total. Nope, there's few total. Yep. Now, so if you got them, see if you could draw them in the line structure. Or whichever ones you got, see if you can draw out that line structure. Yes, that's all. Yeah, if the sticks get stuck, there is a little rubber tube that should be in there. You can use that to pull it out. You have two. All right, so I was impressed with that you got all these. A lot of you got them all, so let's take a look at them. They're all going to be C5H12. And so, of course, there's the straight one where they're just all on their line. Then you can disconnect one of the ends and put it on somewhere else, and you get this one. And then there is the one where they're all connected to the middle again, like that. It's okay, you don't need to get violent about it. So now, what I saw some discussion of, which is good, is this middle one. So let's say like somebody found one like this, and then somebody else found one like that, and then maybe like that. Are those three the same, or are they different? And this is the tricky thing about coming up with isomers, is figuring out whether, especially when we get to the bigger ones, how do you know if the ones that you found are the same or are different? So with those three that I drew, are they the same or are they different? Got some difference, got some same. So we need a way of actually figuring this out. They are actually all the same, even though they all look pretty different. And so let's see how we can maybe figure that out. One way you can figure that out is looking for the longest continuous chain of carbons. So in each of these, we can circle a line of 4 carbons, and we can't get anything longer than 4 carbons. There's a few different ways we can get 4 carbons, but we can't ever get anything longer than 4 carbons. And then also in each of those, we see there's one more carbon coming off of one to the end. So when I have them circled like that, does it make them look more similar? So we can say in each of those we have a line of 4 carbons connected together with 1 carbon coming off of the second one in from one of the sides, either side. And because single bonds rotate, just like in your models, you can spin those bonds around. it gets trickier, trickier and trickier the more carbons you have, because when you kind of flip them around, it really looks totally different. And to be able to say that they're actually the same, you need to be able to look at it like this and say, all right, what's the longest chain and how do we add one? So, well, we can start on this. We'll have to finish this up on Monday, but see now if you can find the isomers of hexane, C6H14. And I'm going to stop you in a few minutes because we're getting close to the end. But let's see how many we can find. If you think you found one, come up and draw on the board. Because one of the things we want to do is compare the way different people draw different versions of one and see if they're actually the same or not. So see if you can see how many isomers of hexane you can find, and then we'll draw them up on the board. I'm not going to tell you exactly how many there are. There's more than the number of pentane. Come draw it. I mean, none of them are claimed yet, so as long as you got one with 6 carbons, it's good. You got a different one? Go for it. It can't, because look what happens. When you do that, you take up a space where a hydrogen would be, and so now that's not going to have the same formula anymore. It'll have the same number of carbons, but it won't have the same number of hydrogen. All right, thanks. So we got one. Go ahead, Pat. Yeah. We want to draw everything anybody comes up with, even if they're not different, because we want to be able then to evaluate whether different ones are different or not. So anything you can think of to draw, because we're running out of time here. Anything you can think of to draw, come up and draw it. All right, he's got another one. Can maybe get one more? Then we'll stop and talk about it for a second before we have to go. One more? Somebody got one more? You don't want to do it? No? Got one more? Thank you. Thanks. Okay, so now our question is, are these the same or are they different? Are they all different? Are they all unique isomers? Or are some of them the same as others? So I'll give you a hint because we're running out of time. 2 of them are the same. You find the 2 that are the same. The others are all different. 2 of them are the same. Let's just number them from the left to right. So 1, 2, 3, 4, 5. Which 2 are different? Which 2 are the same?
Which one? 4 and 5. Oh no.
So this one you're saying? 2 different.
The first and the fourth.
First and the fourth. Nope, those are different.
2 and 4.
Let's look at those longest chains again and see. So if we can circle whatever the longest continuous chain is for each of these. So for this one, it's 4. Oh, it's 2. Yeah, so we might say this is a 4-carbon chain with 2 more carbons coming off of like the second one in from the right. This one, the longest chain is 5, with one of them coming off right in the middle. This one, the longest chain is 6, with nothing coming off of it. This one, the longest chain is 5, with 1 coming off of the second one in. And then this one, we've got 5 with 1 coming off of the third one in the middle. So this one and this one are the same. They're each a 5-carbon chain. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. With the 1 extra carbon coming off of the third one in. 1, 2, 3. 1, 2, 3. But they look totally different, right? That's what makes this a little bit tricky. So if you built a model of one of these, what that means is you could twist it into the other one without breaking any bonds or anything. But to make any of these other ones, you have to actually disconnect and reconnect in a new place. So that's what makes these different. So these are all isomers except for those 2 which are the same. All right, we are out of time. We will review this more on Monday. On Wednesday is acid-base lab. So you can see that on Blackboard. It's pretty straightforward. And I will see you then. Please put the models back in the cases. Anyway, if you have trouble getting the sticks out, there should be a little rubber piece, little rubber tubing in there that you can use to pull the bonds out.